After solving the solenoid problem, the previous example we did, now we are in the another example, and this is example 5.10, where we are going to find out the magnetic field of a toroidal coil. Now, as I said you earlier, a toroid is basically a donut shape, and it is the same solenoid which we have made like a circle. So we have joined the ends of this solenoid, and it is making a toroid. Now we are going to find out the magnetic field of the toroid system or the toroid shape. We know that it is having a uniform winding, and there are n number of turns, and it is carrying a steady current I. Now we will have to understand the geometry of the problem, which is basically a combination of the Cartesian coordinates and of the cylindrical polar coordinates. Because we have different sorts of calculations here, and the very first thing in this problem is to find the direction of the magnetic field. Where's the direction of magnetic field? When I consider solenoid, then solenoid winding is around the solenoid, so current is going this way and the magnetic field is going in the center. And inside the solenoid, the magnetic field is uniform. And now when the solenoid is turned into a toroid, what will be the direction of the magnetic field? Whether it will have some radial contribution, it will have any azimuthal contribution, any axial contribution along the center here. So we are having basically in this toroid example the XYZ coordinates, and for when we consider the source coordinates, then the source coordinates are in cylindrical coordinate form, and we are having R prime, S prime and phi prime. So these are the source coordinates. Like current is the source here, so we are taking the source. Now R prime here, so it is having a symmetric R prime here as well. If phi is going this way, half of the toroid, then minus phi will go this way. So we are having a symmetrical system here. The other thing is that the inner radius of this toroid is R1 and the outer radius of this toroid is R2 here. And here is our observation point. This observation point we have considered in the XZ plane. So from here, from the source to the observation point, we are having the distance is this tilted R. This is our terminology. We are using it like R prime, and R is our observation point, R prime is the source point, and tilted R is basically from the source to the observation point, the distance, we call it a separation vector as well. So starting from here, how we will find the field, we will use the Biot law for finding out this field, and that field is equal, so I can write the field at point R due to current element at R prime is equal to dB, which we will have to integrate, is equal to mu naught over 4 pi, and we have IDL cross, is we did this thing IDL, and this DL will be prime because we are having the source cross this tilted R divide over R squared. This is the Biot law. We have already written this one. And now we will find out the field here. That what the field of, remember one thing, that sometimes we are merging these two, is we can write I cross R, we give a vector, as I have discussed this in the earlier part of this chapter. So we have the observation point in the XZ plane. So the coordinates of this one are, of this point is X and 0 for Y and Z. So this is these are the coordinates of the observation point, and the R prime, we have the coordinates for this one is equal to, so the source coordinate here, this is the source is in this plane we have, so we have the coordinates of this is, this I can write is S prime and cos phi prime, S prime and sine phi prime, and Z prime here. So we have this is the coordinates of the source, and then we have the separation vector R, which is R minus R prime. So I can write the coordinates of tilted R is, these coordinates are equal to X, because from X I will subtract this one, so X minus S prime cos phi prime, then we have Y equal to 0. So 0 minus this one, and it will become minus S prime and sine phi prime, and then Z minus Z prime. So Z minus Z prime is the coordinate. Now what we are going behind? We are basically going behind to find out that in which direction the magnetic field is. And once we are sure about the direction of this magnetic field, then we will have the we will be able to find out the magnetic field inside and outside, or within the toroid. We will be able to find out the magnetic field. Now the current, the same way the current is going this way, so the field is basically going along the azimuthal direction. There are components of this current. The current means there are axial components as well, and there are radial components as well. So both the axial and the radial component, due to symmetry, are cancelling each other, and this we are going to find out that only the azimuthal component, only along the phi direction, they are contributing and they are aiding up constructively, while the axial and the radial components, due to the symmetry, because we are having symmetrical points on both sides, they are cancelling each other. So we will, means from the sense of the problem, this thing is clear that only the azimuthal field is surviving. But we will have to prove this thing mathematically, and for that mathematics, we will go to some rigorous geometrical calculations, and let's start with that one. So we have now the coordinates here. Now if I want to write this thing as a vector and just combine this with this one, so I can write that the magnetic field B at R will be equal to mu naught and 4 pi here, and then this I can write is I being a vector here, and if I make this a vector, then I will have to write this as a cube. because the conversion our vector or our magnitude here, and it will make our unit vector. So this will become our cube here, and then there will be d tau prime on which we will do the integration. So here the integration, and it will make our magnetic field at observation point R. Now look at this one to the this one in bits and pieces, because we will have to look at this one like what's the result of I cross R, and then what about R cube here. We will have to find out these things, and then the integration is a bit difficult, but we will have to see that thing, how we will be able to solve that integration. So here these things are clear, and now we know that the current element has no phi component, because the current is just going around this one and this winding, so it is having no phi component. So I can say that we have the current I is a combination of this is vector I, so we have IS and S unit vector and IZ and Z unit vector, and we have no current phi, no azimuthal component of this, so I phi is equal to 0. And this I can write, this implies that I vector coordinates will be the IS cos phi, IS and cos phi prime, then IS and sin phi prime, because we have the S cos phi prime and S sin phi prime here, and then the Z component of this current here with IZ here, because we know that in Cartesian coordinates the S unit vector is having the coordinates is the cos S vector is cos phi. So we have this S, this unit vector, and this is cos phi prime and sin phi prime, and with the Z is equal to 0. So it is in this one I can write Z0 here. So we are now all set for our calculation. Now what about I cross R then? I cross R vector, I will have the matrix cross product form, and this is let's say like X, here Y, and here Z. So now the I coordinates, let me write them. They are IS cos phi prime, then IS sin phi prime, and IZ here. Similarly, of the R, as I have found there, this is X minus S prime cos phi prime and minus S prime sin phi prime and Z minus Z prime. So we have calculated this one. Let's say the component of this are, let's say AX, AY and AZ. So we will write the AX, AY and AZ components here. And what about this one? The AX component I find from here. So AX Now we know in order to find the x component, we will have to eliminate the row in the column here. So we are having is sine phi, is sine phi prime. This is multiplied with z minus z prime, and then minus, this will be these two and these two. So minus minus plus, and we have iz and s prime sine phi prime. So we have here, if I look to this one, then I can take sine phi prime is common from here, and then we have here the is multiplied with z minus z prime, and with iz here, I plus iz and s prime. So we have the value of ax like this. Similarly, the value of ay. What's about ay? We will have to cancel this point here. So this is multiplied with this one. So is cos phi prime is multiplied with z minus z prime, and then minus this, minus iz is multiplied with x minus s prime cos phi prime. So we have, if I look to this one, then we have cos phi prime here, and then cos phi prime here. So this is x minus this, and we can take a common here, and that is that we can take cos phi prime common from here, and then some terms here and another term here. But cos phi is common from here. Similarly, if I look at az term, then the az term is here. So cos phi and sine phi here, and minus cos and sine phi combination here as well. So let me write that it is sine phi and cos phi combination here. So we have the sine phi and cos phi combination here with this, and then some terms will come here. But the combination is sine phi and cos phi here with us.